Ni hao, and welcome to our talk, Building an Open Source Data Science Platform based around Kubeflow. So, just a quick raise of hands. Who has used TensorFlow before? TensorFlow? All right. I guess half the room. So this talk is basically about how can we move from using TensorFlow towards using Kubeflow towards actually building a complete data science pipeline with all the features from data over to model serving, over notebook sharing, and everything else. It is based on the experience we have with a number of customers, mostly in US, some using Kubeflow, others just using other open source technologies. I'm Jörg. I'm the technical lead for data science over at Mesosphere. I used to be a core Mesos developer, actually same as Gilbert here. Your slide.
I thought you were going to introduce me. No? Okay, so my name is Gilbert. I'm leading the containerization team at Mesosphere and Apache Mesos PNC and committer. Basically, today's talk is about how do we run Kubeflow on Kubernetes and Mesos. So yeah, first couple of slides I'm gonna introduce why do we want to do machine learning and what's the problem we are facing and what's the potential solution and potential future roadmap we're gonna have. So yeah, it's already like the second decade of the 21st century. So we have got more and more data, and data is stored in the data center, and to process those data is way too hard. So people have to do like the convolutions, have to do like the mapping, and then they have to do it again and again. So it's too painful for data scientists because they might probably focus on algorithm, to focus on like machine learning code, and then given the data set, they should be supposed to train the model and then come up with a solution. But the problem here is like, if they want to scale up, there are a lot more problems they need to resolve. They have to manage the cluster. They have to schedule the resources from the cluster, GPU, CPU, and memory, and they have to do the monitoring on their task. So yeah, this is just another slide. So as an example, like we got data everywhere from our life. For example, like auto driving, we get GPU data, we got sensors, we got photos from the other car. So, and data come from each of the vehicle, and we need the data center to deal with all those data, and then data science could come up with a solution like, oh, this is the user behavior. We should improve the way we auto pilot the car, and we need to improve the way, like make the life easier for the drivers. So it's like a batch. So right now it's very close to us. Like we could have the machine learning to develop a deep batch for us, which means like the music might potentially come from computer, and they're all AI developed.
Has anyone actually seen that project? When I saw that for the first time, I was really impressed because it really sounds like Baroque music. So that was kind of like one of my moments, whoa, we have really come very far with deep neural networks.
Yeah, I thought like it's way too early, but surprisingly, like recently I did find out a couple like deep learning project. They make music. They have the machine, they have the computer AI to learn like thousands of machines, and then they have the AI to generate their own music. It sounds not too bad. So, okay, so that's what our data scientists supposed to do. They're supposed to focus on like intelligent machine learning code, and given a data set, no matter it's like large set or not, they should be able to train the data for the model, and then they should be able to run the model. And then they might want to improve the code and then do it again and again. And then finally, they have a precise enough model for their data training. So this is ideal, but not realistic at this moment because we've got a lot of challenge for cluster management. So yeah, this is a hidden technical challenge from machine learning system. So as you guys can see, like only the central black part, it is the machine learning. And for data scientists, yeah, they have to deal with a lot of like operator responsibility, development responsibility, and cluster management. So which is not supposed to be done by them. And we should have some like existing project to help data scientists and make their life easier. So that's what we are doing with Kubeflow. And this slide, you guys might already see this slide earlier this morning in the keynote from Chai Cloud. And I was surprisingly realized that, oh, they have the same slides as us for this one. And basically, it is a good thing to me, at least. It is a good thing. It means like in the industry, in machine learning, in AI, different company, different organization, and open source project, we realized that similar problem. We want to resolve this problem. And that's it. And we get started from here. And then, coincidentally, we find the same solution, Kubeflow, here. Yeah, as you guys can see, like each of these blocks, it might not be easy. Resource management, no matter Kubernetes or Mesos, we have different resource scaling strategy. And people might need to deal with some low-level things like GPU topology to improve the performance. They might need to deal with like the container runtime potentially to provide some more isolation for data scientists. And those may not be the things necessary for data scientists to understand. We expect like data scientists just focus on what they should focus on just focus on like developing the best algorithm for machine learning and then train the model. That's it. Okay, so we come up with a solution, Kubeflow. So Kubeflow unified different training model, and then it come up with the pipeline with different parts of this training distributed system. So it included like data preparation, plus the model engineering from the Jupyter Notebook, and it also integrated. That's the major part from the TensorFlow for model training, for like monitoring, and then it come up with some CLI tooling for debug purpose, and as well as like the model serving from the TensorFlow. This is a quick definition about Kubeflow for folks who never touched Kubeflow before. So basically, Kubeflow project is dedicated to make deployment of machine learning workflow on Kubernetes simple, portable, and scalable. So yeah, scalability is always the biggest problem for system engineer. For distributed system, it's never easy. So you might hear a lot of stories from those big companies like Alibaba, like Tencent, and many other companies like Google, Twitter. So they scale up to like hundreds of thousands of machines and even 1 million of machines. But a lot of work. They might have like 1,000 engineer team to scale that up, to improve the kernel, to improve the core component of their scheduling system, and then they might also do a lot of limitation on the scheduler to improve the performance. So a way lot more discussion about scalability. But yeah, today's talk we're gonna still focus on Kubeflow. So yep. So the next I'm gonna have my colleague Jörg to introduce the detail on Kubeflow and our adventure.
So first of all, Kubeflow was started actually last year. And just yesterday, they announced the 0.3 release. So congratulations to the entire Kubeflow community. It's really great to see. And it was really cool to see the progress they have been making towards that. This is also another talk from yesterday from Aaron and Faye about this last year of Kubeflow, basically. And anyone who is interested in Kubeflow, I would really recommend watching the recording later on. Because we'll focus, in this talk, we'll focus a bit like on what's happening around. We'll not cover so much of the details of Kubeflow itself, more like what are best practices around, what do I need to build like a scalable data science platform and operate that in general. So just a quick question. How many of you have seen this image or actually read that paper? So this is TensorFlow extended, and this was kind of the it's kind of the motivation, or kind of used to be the guiding principle for Kubeflow. So this is about like how Google does machine learning, and it's about the entire pipeline. And a lot of different pieces in the TensorFlow ecosystem have been actually developed from this. And just Kubeflow actually has evolved further from this goal or original motivation. So if we look at it today, and this is what I found really amazing over just 1 year, we are not just focused on TensorFlow itself anymore. We also have PyTorch in there. There's also some MXNet support. We have hyperparameter optimization. We have a lot of other ecosystem projects stepping in here, like Seldon AI for serving, ModelDB being used to store metadata for models. So it's actually not just TensorFlow anymore. It's going back to this original goal we saw earlier about becoming the default kind of pipeline to orchestrate and deploy machine learning pipelines everywhere. Still, even if we have this pipeline, in my opinion, Kubeflow works really well if I'm in a cloud environment. If I'm on Google Cloud, if I'm on Amazon, if I'm on Alibaba Cloud, this works really well because there are still some hidden pieces missing. So if I'm in a cloud, I actually have access to cloud storage. So I can store my data sets, I can store my models somewhere in a persistent fashion. I typically have access to some kind of way to do batch data preprocessing. I have some kind of stream systems where I can actually stream my requests. And while I'm in a cloud environment, I can simply use all of that. Not necessarily for free, but I, as a developer, I don't necessarily have to care about that. Now, many of our customers, many of our users, especially in Europe or environments which are like constrained, which data can be uploaded to the cloud, they actually try to build something similar in their own data center. So there are a lot of open source tools available. So for example, Spark is a really great tool to do data preprocessing, or in general, like the entire Beam integration, if I want that more abstracted. HDFS is a great data store for unstructured data. I can use Kafka to pipe my requests towards my serving layer. So it's just, all of a sudden, once I try to build that in my own environment, so in an on-prem cluster, I start to have to consider all those different components missing, which I just get for free in a cloud environment here. So in the end, so this is typically like the advanced picture. So this is what we see people building over years, and most likely not having all of that. But let's just simply go through what different steps are actually needed in such kind of pipeline. What I really liked in the keynote this morning, it touched upon some points which are very dear to me, especially the challenges. So you might actually recognize some of those points from this morning's keynote. So it all starts with like data and streaming. I need to have access to data sets. At best, I have like versioned access to data sets. There are a number of companies actually trying to get better support there because Git doesn't really work for large files. There's, for example, .science. I've seen some of their people here as well, which give me a versioned access to data sets. I can also just have a data stream, so it doesn't have to be fixed data sets. Many systems just have streaming data, and so I could have like a Kafka stream of data, which I might actually also use snapshots for training. And so this is kind of the first basis layer, but it's really important, and we'll come back to some more details here in a second. The second part, and this is where my data scientist really wants to focus on, this is the model engineering. This is the data preparation and model building. So this is really typically Jupyter. How many of you know Jupyter as a project or have used it? Some. For those of you who haven't, I would really recommend it. It's a really nice way to get started with data science without having to worry about too many of the details. And so, as mentioned, this is like where my data scientist, he can go in, he can prepare that data set, he can extract features, And then the next layer is actually model training. Model training, this is really where most of the resources, GPUs, TPUs, CPUs are flowing in, where I have different hyperparameter runs, and this is something where typically more like DevOps people should come in because they actually understand distributed training and distributed computation. Once I'm done with training, I have a number of models which I need to store, and I not only need to store the models, but even, or equally important, I also have to store the metadata of those models. What was the train accuracy, what was the validation accuracy, so all those different statistics, because here I later on from the model management layer, I actually have to select the models I want to serve for production workloads. And that might depend on questions like, give me the best performing model for a GPU environment which takes less than 0.5 seconds to do inference. So I need a lot of this metadata to actually choose the different models I want to serve later on in production. So this is the simple pipeline walkthrough, but around that we have a lot of other pieces. Already this morning, it was mentioned that we need two different kinds of monitoring systems. The first one is kind of for the models, for the data science or data scientists themselves. And this is focused, on the models, on the model accuracy. And this is typically something like TensorBoard. Secondly, as this is becoming a fairly complex architecture, we also need some systems to actually monitor this architecture itself. All right, then if we continue down here, we mentioned like the data is very, very important. And data scientists, they typically spend 60 to 70% of their time preparing their data sets. So for example, cleaning up the data sets, converting everything to like a common, hopefully metric system-based format, maybe extracting specific features. So if I'm building a fraud model, for example, I only care about that I have some representation of a user, and this can actually be shared amongst different data scientists. And this is why a component such as a feature catalog or other systems, they also call it feature stores, become really important because, as mentioned, if I invest 60 to 70% of my data scientist's time in developing those features and cleaning the data sets, this is something which should be shared between different data scientists. The second part is actually all this work here. This is fairly automatic. So a data scientist shouldn't have to worry to start his training runs or anything else. And from traditional software engineering, we actually have techniques to deal with that. Continuous integration, maybe even continuous delivery if we want to deploy the models later on into production. So having some kind of CI/CD pipeline here really is taking off a lot of load from the data scientists to have to train that manually. And it also, which we'll see in a second, helps us with reproducibility. The other piece, which is, we already mentioned, like those Jupyter Notebooks, they are very, very helpful and very, very important. So I also want to share those notebooks between different people. And so something like Binder, those of you who haven't seen Binder, it's a really cool open source project, which basically allows me to store an IPython notebook, so a Jupyter notebook, to GitHub, and then simply say, gives that link to anyone else, and they can simply run it without having to spin up any infrastructure. Binder, or there are also like open source projects running that, like called MyBinder, for example, or Google also has something very similar. They give you an executable form of your Jupyter notebook. I can just send that to Gilbert here, and he doesn't have to set up Jupyter itself. He can just run that from this web link, which is really cool. The other thing I actually really want to share are my trained models. So having something like TensorFlow Hub or a model library is really useful, first of all, for sharing the trained models, but also later on for transfer learning. So transfer learning, I would go in, I take a fully trained model like ImageNet or something like that. I go in, I take away the last few layers, and then I specialize that to my specific data set. But using this pre-trained model, it really reduces the amount of time and resources I have to invest into training. And it also reduces the data set size I actually need to train that, because most of the base features already been covered by this pre-trained model here. So having a platform where I can actually share and reuse models, retrain models, is also quite important. Last, underneath, we actually need something to manage all those resources, to manage all those different distributed systems. So if we just count, we got like Kafka, Cassandra, HDFS. Jupyter is more like a container service, but here we got TensorFlow, Spark, PyTorch. So we actually end up with a large number of different distributed systems, which we all have to manage. And this is really hard for like a DevOps person to set all this up in just a manual fashion. So having like a layer for, first of all, the resource management, and then also for service management is really, really important and really helps us to set up such kind of pipeline. All right.
Yeah, so I just one quick when we talk about like the challenge of like having different like machine learning framework, deep learning framework running on the same cluster, we did have a customer like suffer from like, oh, when they realize they want to run Spark, which is like best job and greedy framework, and then they want to run TensorFlow, while they also want to run the Cassandra and Kafka on the same cluster, and then have one single cluster to manage all those distributed systems and machine learning workload, and that's really painful for at least for data scientists to manage the whole cluster, because like some of the tasks, they are greedy and then they will occupy all the resources. And for data scientists, it's really hard for them to realize, oh, we need to introduce more like scattering strategy to make it more scalable.
Actually, this is what the next slide is about. The data scientist himself, he wants to be the superhero writing really cool code. And he shouldn't have to worry about distribution or distribution strategies. He should really be able to focus on his models. And this is why we typically see different personas being introduced. And so he needs a side gig helping him to still be this really cool superhero. And this is typically like today, it's either referred to as data engineer. It's more like a DevOps person, which is really helping this guy in controlling the entire infrastructure with helping the data scientist to be able to focus on his models. The next challenge is actually then data quality. As mentioned earlier, typically this is what most people underestimate if they start with that first MNIST model. I suppose everyone who has started with TensorFlow has probably done like this MNIST example, right? I download a pre-cleaned data set, I go in there, and I can directly train my model. But in reality, unfortunately, this is not the case. So demo data sets are a fortunate exception here. But typically, I really spend a large amounts of my time as a data scientist in preparing my entire data quality. And the kind of promise of deep learning, especially, is that everything is being derived from the data itself. So just keep in mind, if your data is of bad quality, your model will be of bad quality as well. The other important lesson is, and I actually seen that at a user side, is if you update your procedures, your pipeline to do the data preparation, you also need to update the same procedure to your real life data coming into the serving layer here. So actually what those people did, they came up with a really cool way, a new way. So they had an existing pipeline running in production, and then they stepped in and improved the way they were cleaning and preparing their data sets. Their models had much better quality, much better accuracy. But once they deployed them to production, it had really bad quality. What happened? They didn't update the data cleaning procedures in the serving environment for the live production data. So that was still kind of the old data format, which obviously didn't match to those new models here. And so this is actually, this was a slide I was looking for earlier. This is actually this division of labor. So if we jump back here to our like superhero data scientist plus his sidekick, this is the earlier image we saw with all the different challenges. And now we actually can divide this between different personas. So the data scientist, he can actually focus on writing his machine learning code, on preparing data, on exploring data, on extracting features. Maybe he needs to do like some model monitoring, but overall he can really focus on being a data scientist. And most data scientists I know, they have more like a mathematical background, so this is what they like doing. And now we have those other people like the data engineer, data ops engineer, and they can actually help with all this stuff around, which often also requires more knowledge about distributed computation. And yeah, this is kind of this rise of this data ops, data engineers. The people I've seen, it's really, really hard to find them, but they are combining two key skills. First of all, data science, and secondly, they actually understand distributed systems fairly well, because this is the challenge. They have to match this world of data science with the distributed systems engineering, with actually controlling all those different systems we've seen earlier. If you want, it's kind of like this DevOps person, but for like data science in particular. This is actually the original paper. It's the first publication on software engineering. There was a mentioning before, but it actually, software engineering is something where I feel we can learn a lot for data science. I feel data science right now is in a state, software engineering was like around 1968, where everyone was doing stuff very ad hoc. Everyone was trying to figure out his or her own ways of doing things. And so I would actually pose that question, do we need something similar for data science? Do we need something like data science engineering principles? So a systematic, quantifiable approach to the development of models, and also then the testing of models and everything around, which we actually have learned in software engineering. And people like Ian Goodfellow, for example, they also have similar opinions. So this is what we are currently working on in the Bay Area with other big ML users, such as Uber, and other big companies doing ML, which names we are not allowed to mention on stage. I always feel this first challenge, if we look at software engineering, is like requirements engineering. How do I come up with the requirements I need before I start developing my model? And there, having talked to a lot of people, the most important question someone should ask if he's told to develop like a deep neural network is that, does it actually make sense? I currently feel that especially neural networks, they are very, very powerful, but we apply them to problems where they don't really match. So especially if, for example, if I have a small data set which might not be sufficient to train an entire neural network, if it's of bad data quality, or actually my function is also pretty similar, something like support vector machines or even like logistic regressions can be very, very powerful. So we shouldn't just blindly use deep neural networks because this is what our CTO has just read about. Other requirements I should gather is like, what is actually my target and serving environment? Will I serve that in a car where I need like sub-second response times? Will I serve that in a large cluster where I have a lot of GPUs available? So what is kind of the resources I have in my serving requirement where later on I will use that model? And also, what are the guarantees? So what timing guarantees do I have to have? Other questions, are there pre-trained models available? I believe most of us shouldn't actually develop new models. People like Google or research have actually come up with a lot of really cool model architectures, and there's a lot we can actually reuse here. The next biggest challenge, and this is where I see most companies actually fail, is reproducible builds. Still, data science right now is a very ad hoc process. Data scientist goes in, he's playing with the data, he's playing with his model. Once the accuracy looks good, he goes over to the DevOps engineer or some kind of ops person and tells them, here's my model, please deploy that to production. And so what we've seen is that even just going back and say, can we retrain this model with the same data set or with an updated data set, often becomes a challenge in different environments. So especially if you have to deal with regulatory requirements, for example, in finance or healthcare, this is like a big challenge. And so two projects which I really find helpful there, when I first prepared that, Kubeflow pipelines weren't out there yet, but they just announced also Kubeflow pipelines and mlflow. Both of them, they give me a way to get an artifact of my data, of my entire pipeline flow, so I can actually go in and reproducibly train that. The other aspect which I find really important here is again the continuous integration part, because it actually forces me to create a reproducible artifact. So if the entire training process is being taken care of by my CI/CD pipeline, I actually have to create a reproducible artifact because otherwise it cannot be trained. Just real brief, as probably more people are familiar with Kubeflow pipelines, mlflow is a project by Databricks, the guys behind Spark. And the sub-project here I like most is actually the projects part, because it gives me a packaging format. It's very, very simple, but it gives me a packaging format for reproducible runs on any platform. So I can go in and just retrain my model. Kubeflow pipelines does something similar, but as said, you can use both. It probably depends a little on also the surrounding parts. And so then, and this is again coming back to this division between different personas as well, is again, so here we have the data scientist up here. So he can deal with his data set, he can use his Jupyter Notebook to explore his data, to come up with a model, and once he's done, he's actually currently, this is typically a Git commit, but once he's done, he does a Git commit from his Jupyter Notebook, and this is actually triggering the CI/CD pipeline. So we have taken care of all the distributed training, model testing, model optimizations, model storage, and if I actually want to do also continuous CD, I can even then put it into serving into production with that. So this is for those of you who haven't seen Jupyter. This is kind of what Jupyter looks like. So this is the first view if I go in. And I can simply, in the web browser, I can write all my Python code. I can write my Scala code for Spark. I can write Java code. So I don't have to set up my own environment. And I can then also execute it from there. I can export those notebooks. I can share them. So they're just a very nice way for data scientists of not having to deal with setting up infrastructure and actually being able to focus on their real work. The other challenge about this data quality or data pre-processing, and this is the feature catalog we saw earlier, and this is basically about this work we want to share in cleaning and preparing the data set, which we can, for example, if we are in Kubeflow, we often, or in TensorFlow, like we do TF transform. But once we have done that, and it ends up in this like one big pipeline, I cannot simply share that with other people. So everyone who's coming up with like a fraud detection model or who wants to use user data has to come up with his or her own way to actually prepare all this user data and come up with a user data representation with a user data feature. And so therefore a feature catalog is really useful to share that. So it's kind of like a pre-processing cache. I can even cache the prepared data sets and then also discovery components that other people can find and reuse that. And a really highly recommended resource is, it's called Michelangelo by Uber. So they actually, in their blog post, they talk a lot about this feature catalog. Other thing, again, are model libraries. So in normal software engineering, we deal a lot with libraries. We should do something similar in data science. So we can reuse pre-trained data sets. We can use pre-trained embeddings. We don't have to come up with everything from scratch. We don't have to train everything from scratch. So also this is something I've seen organizations set that up in their organization and simply share all this. And it really boosted the productivity. And it also reduced the amount of resources they had to spend on compute, GPUs, CPUs. I got 1 minute? All right, then let me jump through here. Let me see. All right, hyperparameter optimization, also very important. But there was actually, this is being covered, all of the previous slides are covered in the Kubeflow talk itself. One other thing I would really highlight and everyone should think about is model optimization. So once I've trained my model, I actually need to go in and optimize it, for example, for different serving environments. If I want to have a neural network running on a mobile phone, the normal output of TensorFlow probably is going to be way too large and way too slow. So I can go in, there are different transform steps, but this is something you should really consider. And you can also optimize that for different serving environments. You might produce one model which is running on CPUs, one which is running on GPUs, and maybe one which is running on your mobile phone. Challenge, challenge. This is actually what Gilbert mentioned earlier, like this resource and service management. This is also very, very challenging as I have to deal with all those different distributed systems. What I would typically do in a cloud environment, I spin up different virtual machines for each, but this is actually wasting a lot of resources. So if I'm having like one VM for each of those, this is going to not lead to a very resource efficient cluster. So I should actually come up with a way. And Kubeflow also has some really cool tools in like auto scaling. For example, the TensorFlow cluster, which can really help me for like performant resource management. All right, and this is basically leading to this entire pipeline. If you have any more questions, feel free to either talk to us, or we also have like a white paper you can download from the slides, which is going in some more details. I would actually love to close with like my wish list for the next Kubeflow iterations. As yesterday we announced like the 0.3 release, and the roadmap also looks pretty cool. First of all, it's really better CI/CD integration. Seeing what's happening with Argo CD is cool, but it should really be easier to integrate with different CD environments. I should be able to share my notebooks with other people. And what I also believe in, we actually need a common metadata layer. Having different components storing the metadata, for example, for the like ModelDB, we also have metadata which we gather from experiments. So I feel having a common metadata layer across this entire infrastructure is going to be so helpful in sharing that data and being reproducible. Last thing, but that was also announced yesterday, is actually like a governance model, which they're currently considering. So really to have a bigger community around that, because I feel Kubeflow is really helping us in having a reproducible standard way to set up machine learning pipelines. Thank you so much.